So in this lesson, we're going to be taking a look at transformations of functions, and in particular, we're going to take a look at the transformations of the trigonometric functions sine and cosine. We've been starting to look more and more just at the graphs of the parent functions, and we've done some transformations based on tables of values and based on maybe descriptions of more physical situations. But what about just a pure transformation from the equations? Just to refresh your memory, here are the graphs for sine in blue and cosine in red. Those are the parent functions. And just to remind you of something that we've covered before in this course, and hopefully you've covered yourself before coming to this video, which is the idea of just function notation in general. If we start off with a generic parent function y equals f of x, then we can start to apply transformations to that function, and the kind of the standard convention for what those transformations look like, we use four parameters: a, k, p, and q. In some conventions, you'll just see people using a, b, c, and d. Those are interchangeable and they're all perfectly fine. The important part here is to remember that our function, in this case f of x can be equal to the sine of x. That's what we have in this case. F of x is sine of x. But we can also have our function f of x can be equal to the cosine of x. And if that's the case, then we assemble this the exact same way that we would any other function. If f of x is sine of x, then I can start to put pieces together. So let me just show you that here. If f of x is equal to, well, since I did it in red, let's stick with cos of x. If f of x is cos of x, then that means that f of whatever's inside this bracket, so that means f of kx minus p is equal to, well, wherever I had an x before, I replace that. So that would be the cosine of k multiplied by x minus p. Those are the horizontal transformations. And then I could also multiply that whole function by a. So that's a outside the function bracket. And then I could add q. And again, this is outside the function bracket. So of course, a outside the function bracket multiplies the function itself. And then once we're done with that outside of the function, we have our q value. Again, hopefully this is a review, hopefully a very familiar review. Some people might need their memories refreshed on this. For any function that's being transformed, if it's written in this standard form, you've got a, k, p, and q. A are vertical transformations. A will give you a vertical reflection if it's negative, and vertical scaling. So that would be stretch or compression. K is a horizontal transformation. If k is negative, you have a reflection. Otherwise, if k is not equal to plus or minus 1, then you have some sort of scaling, stretch or compression. P tells you about a horizontal translation or shift to the left or right. Q tells you about a vertical translation or shift, which would be up or down. Another very useful transformation to understand is how individual points are transformed. And so this is the process that you can go through. Most of the time I only focus on the first to the last, but as I've got it written here, this is how each one of these, so if we numbered these 1, 2, 3, and 4, that's what each of these transformations is referring to, each of these stages as we progress. So this is what the A does. This is then what the K does. This is what the P does. And this is what the Q does. Okay, now in order to transform a function, you probably need to have a fairly good idea of the parent functions. Now, if you've done this enough, it doesn't take too long to become quite familiar with the shape of the parent functions. This, for example, is the parent function for y equals sine of x. It has a maximum value of 1. It has a minimum value of -1. This is 360 degrees, which would make this halfway at 180. Half of halfway, 90. The other half between 180 and 360, 270 degrees. We can also very quickly and easily do, or at least we want to get to the point where we quickly and easily can do the parent function for cosine. That was not very nice. Let's try that one more time. Not great, but it'll have to do. That's 360 degrees, midway 180 degrees, 90 degrees, 270 degrees, and +1 and -1. Now, how do I use the unit circle to do this? Remember your unit circle, this is 0 degrees and this is also 360 degrees. 90 degrees at the top, 180 degrees at the negative x-axis, 270 degrees at the negative y-axis. Let's see if I can go ahead and actually put a nice shape in here. I don't want to look too long. I don't normally use the shapes, which is why I don't have it in my menu. Maybe I should think about adding it. Oh, let's see. The magic pen should let me do a shape, won't it? Nope, not what I wanted. Okay, so let's go ahead. I'm just going to do a rough circle. What are the coordinates of this circle? Assuming that this is a circle with radius equal to 1, then this would be the point 1, 0. This would be 0, 1. This would be the point -1, 0. And this would be the point 0, -1. And then we remember that any point can be written in terms of an x-coordinate being cosine of the angle theta and a y-coordinate being the sine of the angle theta, where this is the angle theta. So as I travel through angles, starting here at 0 degrees, so what is cosine of 0 degrees? It's equal to 1. It's equal to 1 right there. What is the cosine of 90 degrees? It's equal to 0. And there it is, equal to 0. That's not a very good 1 there. Let me rewrite that. So that's 0, 1. And so on. So each of these coordinates. So what does cosine do? Cosine goes 1, 0, -1, 0, back to 1. What does sine do? Sine is the y-coordinate. 0, 1, 0, -1, back to 0. And that's where each of those graphs comes from, or those sketches in this case. So using those, I've already done this, I've already shown this to you, so one more time. Sine starts at 0, and let's see, I'm going to put 1 there. And what did I do? That was 3 6 squares, 6 squares, -1. This would be 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Sine starts at 0, then it goes to 1, then it comes back to 0, then it goes to -1, and ends at 0. Cosine, I could do a better job of that graph, but that's not really the point of why we're here. Cosine starts at 1, then it goes to 0, then it goes to -1, then it goes back to 0, and it ends where it started at 1. That's terrible. That I have to redo. Okay, so how do we graph these things? First of all, we can graph these using this property. So this is the summary with all of the transformations in place, which is the point x, or sorry, the x-coordinate turns into x over k plus p, and the y-coordinate turns into ay plus q. That's one way we could do it. The other thing we can do is actually look at these key properties. So think of things more in terms of amplitude, period. This new idea, we haven't really talked about this, something called phase shift. So amplitude and period, well, we've spoken about these before. Amplitude, yes, we've talked about period. The idea of a vertical reflection and a horizontal reflection, those should be fairly familiar to you. We've talked about the axis of the curve, which is your vertical shift. So this idea of phase shift, this is new. Also, I've got a little bit of a kind of a handy little formula here. The period of your new function can be written as 360 degrees divided by k. And so I will talk about that in a moment as we do some examples. Now the phase shift, I'll deal with that when we get to an example using that, which is the best way to illustrate it. But just remember, keep in mind for now that the p-value is your left-right shift. Okay? So that phase shift is the idea of shifting it left and right. That's why we talk about the starting point. Okay, so let's start off with, I have all of this in a handout, all of these grids already laid out for you with all of these. All you need to do is work on these. You can get those from the web page. Here is the parent function of sine already included. You can see the starting point of sine is at 0, 0. And then after 360 degrees, that's where it ends up again. The parent function for sine goes from 0, 0 to 90 degrees and 1. So it goes into the positive to start. Now we take a look at this, and the only transformation that I have here is the 2 in front. And that 2, I've got room to write that. That's your a value. So in this case, a value is equal to 2. And there's only one transformation here. That would be a vertical stretch by a factor of 2. So what is this graph going to look like after I stretch it vertically by a factor of 2? And I would once again focus on the key points we talked about graphing for the parent function. So I'm going to focus on these 5 points. I might bring in other points if they're really necessary. Those other points would be from the unit circle. But these 5 points at 90-degree intervals are the really important ones, I think, for doing this. So a vertical stretch by 2. So that means don't forget, a vertical stretch by 2, that means it's going to be the y coordinates that are going to change. I've got too much graphics on this page for my poor little CPU in this tablet computer. So what happens when I multiply the y coordinates by 2? Well, here I have a y coordinate of 0. And so I end up with exactly the same thing. I'm going to indicate the new points with x's just so that we don't confuse them with the blue dots. What happens here? My y coordinate is 1. It doubles, which means that's my new y coordinate. My y coordinate here, notice the x coordinates aren't changing. There's no horizontal transformation. My y coordinate here is 0, which means 0 times 2 is still 0. Negative 1 times 2 is negative 2, and 0 times 2 is 0. And so now I end up with my transformed graph. And I end up with that. And it has been vertically stretched by 2. Now, another way that you can think about this is that the amplitude used to be 1. So the amplitude, if I were to draw a couple of lines and say, well, the whole graph has to be between these lines. There's an amplitude of 1 for you. But now the amplitude has doubled, and so that means from the center line to the maximum has to become 2, and from the center line to the minimum has to become 2. I quite often, when I do these dotted lines like this, I refer to them as an envelope, which is I'm drawing a set of lines that contain the entire function. It's useful to do this in conjunction with the axis of the curve down the middle. And so now you can really clearly see, you can see the amplitude of 2 right there. You can see the amplitude of 2 right there. Okay, how about this one, the cosine of 3x? So I've got a parent function of cosine already provided. In this case, I have a k value. I have a k value equal to 3. A k value of 3, that's a horizontal transformation, but this is a horizontal compression. So this one is a horizontal compression by a factor of 3. And the way to think about that is any point xy. The reason why we call that, this is x over k, but in this case that's going to be x over 3. There's no p-value, and then the y value stays the same. This is why we call it a compression. Even though k is equal to 3, the transformation is x divided by 3, so that's going to make it smaller. Okay, so what does that look like? I'm going to take those 5 starting points, and I'm going to take their x coordinates, and I'm going to divide that x coordinate by 3. So in that case, I'm going to be dividing the angles. So what's that going to look like? I'll switch to a different color here. This point is 0, 0. The x coordinate is 0. 0 divided by 3 is still 0. So this does not change. This is the point 0, 90. I'm sorry, 90, 0. So maybe it might be worth it here in this case to actually write it. 90 degrees, 0. We have to take the x value, which is 90 degrees, and divide it by 3. So it goes to 30 degrees. The y coordinate stays the same. I've got a convenient scale here. This would be 30 degrees, so this point has shifted to here. The next point is here at 180 degrees, 0. Divide that by 3, and that becomes 60 degrees, 0. So you can see this point transformation still very useful. So 180 degrees now is 60 degrees. This next one is 270 degrees, 0. This was 180 degrees, -1. I'm sorry, I miswrote that. And so that goes to 60 degrees, -1. This is 270 degrees, 0. Divide that by 3, and it goes to 90 degrees, 0. So 90 degrees, 0 would be right there. And then finally 360 degrees, I might as well finish off. I'm not going to write them out for every one example, but in this case I thought it was important. 360 degrees divided by 3 leaves me 120 degrees. But once again, I'm so focused on having a y coordinate of 0. 360 degrees, 1 goes to 120 degrees, 1. And so we end up right there. And so my new transformed graph looks like that. And so it has taken the original graph and it has squished it by a factor of 3. It is now 1/3 as wide as it was before. Now this is a good time for me to mention what I said before about the period. I mentioned that the period formula is 360 degrees divided by k. But if you think about that, that's no different than what we had here with the x divided by k. So 360 degrees in this case divided by k divided by 3 is of course equal to 120 degrees, and that is the period. So that is a period of 120 degrees. Okay, sine of x plus 2. Now we could continue to do this. we could continue to do this just with raw transformations using the points. But another way to look at this, which I find is quite often quicker than transforming all of your points, is to start off by looking at some of the key features. Now, the vertical features are the easiest ones to just draw in, because you can see I can do that here. I've got the axis of the curve, and then I have the two envelope lines to represent a visual representation of the amplitude. In this case, this value, I think I'd rather have blue, this is my Q value. So this is Q is +2 in this case. And a Q value of +2 means we have shifted up by 2. You could do transformations of the points, but the other thing you could do is you could just say, oh, well, that means that the top of the envelope has moved up by 2. The axis of the curve has moved up by 2. And the bottom of the envelope has moved up by 2. Since nothing else has happened, no other transformations, that means our starting point here has moved up by 2. And all of the other key points have also moved up by 2. Notice that the points that were on the center line are still on the axis of the curve. It's just everything has shifted up. And then go ahead and create your smooth curve. And there I have my sine curve shifted up by 2 units. Now, here's where I'm introducing this idea of a phase shift, and the phase shift comes from a horizontal transformation. Now, this says x plus 90, but remember the standard form of this is x minus p. So this actually tells me that I have a p-value of -90 degrees, and that means my whole graph has shifted left by 90 degrees. And that's what phase shift means. Phase shift is basically describing, and in particular, it's describing where your starting point for the graph has moved to. So in this case, my starting point, so my start of this graph is the point at 0 degrees, and it has a y value of 1. Because of the phase shift, my new starting point is going to be at -90 degrees, comma 1. Now from there, so once again, I'm going to use more key features than point-for-point transformations. I just did this one. The axis of the curve has not changed. The amplitude has not changed, which means I can go ahead and draw my envelope in. You don't need to do this. It's just a visual reference. I wouldn't bother doing this in a lot of cases. This starting point has shifted to the left over here to -90 degrees. And so that puts this starting point is right here. And then I know that for cosine, since I don't have any other transformations here, the period is still 360. And so my ending point, instead of my end being here at 360 degrees, my end is going to be over here at 270 degrees, because it has also, so this one has shifted over to there. This point has shifted over. As a matter of fact, everything has shifted over to the left. So I have a point every 90 degrees in the pattern that I know that cosine follows. And I end up with a curve that looks something like that. And if you take a look at my red graph representing one period, and you take a look at the, well, you take a look at a single period from the dashed graph, you can see the whole thing has shifted to the left by 90 degrees. Y equals negative cosine of x. In this case, we have a leading value. It's actually an a value. The a value is -1. Now the only transformation here is a reflection. So this is a vertical reflection. And so that means all of the y coordinates are going to take on negative of whatever they currently are. So in this case, the point 0, 1 becomes 0, negative 1. This is 90 degrees, 0. The y coordinate 0. Well, a reflection of 0 is still 0. Here, the y coordinate's negative 1, so that means that the reflected point is at positive 1. This one at 0 stays at 0. Here we had 360 degrees, 1 becomes 360 degrees, negative 1. Now something it doesn't work very well. I've mentioned before that the digitizer here struggles when I have graphics in the background. But one of the things that I've talked to my class about is when you're trying to graph sinusoidal functions, it's not a bad idea to put your curves in at the top and bottom in advance. And then you can just smoothly try to connect those together. I did a pretty bad job there, actually butchered it a bit. So let's try it one more time. I did a better curve there without the help of the advanced curve. There we go. So that's not bad. And this is a vertical reflection of cosine. It's very important that you are very clear in your mind about the parent functions for sine and cosine because they won't always be given to you. Okay, here sine, move this down a little bit. Here we have sine. In this case, the value we're looking at, the coefficient we're looking at is a k value. In this case, it's negative 1. So you notice that I'm just dealing with single transformations at a time so far. So this would be a horizontal reflection. So that means that my x coordinates are going to go from positive to negative and negative to positive. Now actually the parent function that I provided here, I could have done a better job of it in light of this particular one, but we'll make do with what we have. So let's start off with the point 0, 0. The x-coordinate becomes negative. Well, the x-coordinate 0, so the x-coordinate is still at 0. The y-coordinate's unchanged. Here, the point is 90 degrees, comma 0. The y-coordinate's unchanged, but the x-coordinate has flipped to negative 90. And why did I'm so obsessed, I can't get 0 out of my head even when I'm actually locating it at 1. Okay, so I have a reflection there to negative 90, comma 1. What about here? 180 is the x-coordinate, so the new x-coordinate is at negative 180. Now, I can't go any further. I can't go any further to the right because I've run out of scale, but I could have gone to the left as well. So here is negative 90. Negative 90, negative 1 is going to reflect to 90, negative 1. And here is negative 180, 0, which is going to reflect to 180, comma 0. And so we end up with that. Now I could continue that. Let's continue that in another, just because I didn't do the points for these. So what we would end up with now, if I continued, would be that and that. And that's actually really a cool pen. I think I need to use that more often. Okay, so there is a horizontal reflection of sine. Now, because of the particular properties of sine, and I'm just going off on a small tangent here, you might notice in this case that the sine of x, okay, if I take the sine function and I reflect it horizontally, actually I'm not going to write what I was going to write there. If I reflected it horizontally, that would be the same as if I reflected it vertically. So now what I'm going to actually write is that the sine of a horizontal reflection is the same as a vertical reflection of sine. And if you remember, when we talked about symmetry, this is the property of an odd function. Odd meaning symmetry. So this is a sine is a function that has odd symmetry. It's also known as rotationally symmetric. If I rotate the sine function through 180 degrees, I end up back at the same function again. So this is a definition that the horizontal reflection and vertical reflection produce the same effect. That is a result, or that is an indicator of odd symmetry. I don't know if that tangent was worth it. Okay, now we're introducing multiple transformations. And so first of all, let's list those transformations, and we'll talk about, once we've listed the transformations, then we can obviously transform points, but I also want to take a look at the effect on key features. So here I have an A value of 2. I have a K value of 1/2, and this outside the bracket, that would be a Q value of -1. The A value of 2, it's +2, so this would be a vertical stretch by 2. The K value, this would be a horizontal stretch by 2. And this is a shift down by 1. So, and you could do this. You could take xy and transform every xy into x over k plus p ay plus q. Perfectly good. You can do that. What's another way to look at this? This graph is going to have an amplitude of 2. That's the A value. Instead of an amplitude of 1, it's an amplitude of 2. The period, which is worth writing out, is going to be 360 degrees divided by k, but that's 360 degrees divided by 1/2, which is 720 degrees. So the period has doubled. So this horizontal stretch has doubled the period. And then the axis of the curve is going to be along the line y equals -1. So I'm quite confident that people, if you've understood transformations, you should be able to do this one. So let's look at it in terms of key features. We always want to start with the axis of the curve, because it just, everything else follows from there. It's kind of like an asymptote. So if the axis of the curve is at -1, it's going to be between there and there. It's going to be centered on that. The amplitude is 2, which means I also have an envelope line 2 above, and I have an envelope line 2 below. There is no horizontal shift, so that means my starting point is the same relative to the axis of the curve. So what does that mean? That means that this was a sine curve, so my starting point was on the axis of the curve along the y-axis. Now my new starting point is also on the axis of the curve along the y-axis. Now, the fact that the period is doubled, normally on a parent function we go 90, 90, 90, 90. We go up by increments of 90. But since this thing has, you can either think of it as horizontally stretched or that the period is twice as much, then that means every time I take a step, the steps are now double in size, 180. So normally sine goes over 1 and then up. So when I say over 1, I mean over 1 step. So we're going to go over 1 larger step and then up. And then it's over another large step and then back to the middle. And as you can see, that's it. I can't fit any more on this part of the graph. I could also have taken a big step to the left And when we take normally on the parent function, it's a 90-degree step to the left and down one. So this would be a bigger step, 180-degree step to the left and down, in this case, 2. Don't forget, all of this is based off of the axis of the curve. And then do your best to start your curve. So we don't get a full picture of the graph here. We actually only have, we have 3/4 of a full period here. But that's the scale that we were given to work with, and so we do our best to fill that in as appropriate. This may be the last example, now that we're getting into these more complex transformations. My A value in this case is 1/2. My K value is equal to 2. And I have a Q value equal to -1.5. And so we could once again, well, let's at least document what these mean. This is a vertical compression by 2. This is a horizontal compression by 2. And this one is a vertical shift down 1.5. In terms of key features again, let's start with the axis of the curve. From the center down to -1.5. How big is the envelope? It used to be an amplitude of 1, but now the amplitude is only 1/2. So my envelope is going to look like this. So it's now vertically compressed. No shift, no change in the phase shift. And so that means my starting point now, be careful here. First of all, check for any reflections. Cosine parent function starts at 0, 1, so it starts 1 unit above the axis of the curve. This is +1/2, so that means it starts 1/2 unit above the axis of the curve. Now, in particular, I want to pay attention to this. That means, what is my period? My period is 360 degrees divided by 2, which is the K value. That means my period is 180 degrees. So that means this will fit quite nicely. This point has to be repeated here at 180. Halfway in between these two, it's going to be at a minimum. This is where familiarity with the parent functions come in. And then halfway, now my scale's a little bit awkward for this because halfway between 0 and 90 is 45, but I can go halfway between these two grid lines. And so I end up with those two. And now I draw a nice smooth curve. I can do a better job of that. So there is a single period, and if I wanted to go further, I could put another point there, and there, there, and notice that now that's 2 periods that I'm showing. And I could extend this way. I could also have extended it in the negative direction. Sometimes a question will specify how many cycles or over what domain you're supposed to draw your curve. I haven't done that here. I want to really focus more on the transformations than to get bogged down in some of those details, but those details do come up. You should expect those. And so you could have been asked to do something like this as well. But sometimes you'll just be asked to draw a single cycle, which is what I did there in blue. Okay, so that's it for a refresher on transformations and a look mostly at fairly simple transformations, but those last 2 examples are good examples of some more complicated transformations of sine and cosine.